So cool guys, today we are going to study about tree routing. We already had a session on DP on trees, but now we finally want to get started with tree routing. So we are going to discuss this problem from CSES problem set, and the problem is tree distance 2. But before we actually start with the problem, let's just try to understand what tree rerouting is in general. Then we'll come to this problem, and then we'll try to understand that how we can utilize it over here. So tree rerouting basically means that let's say you are having a tree. Okay, why isn't the tree coming up? Oh, that's weird. Okay, cool. So this is the tree, let's say, right? Now, if I ask you that get me, let's say, get me something considering this as the node, right? So get me some answer considering this as the root node of the tree. So you'll be able to do that, right? Then I ask you that, okay, get me the answer if becomes the tree node. Now, if this becomes the tree node, your tree basically becomes like this, then you'll have something of this sorts, right? Then you'll say, okay, I'll run the DFS algorithm on this also, or I'll use my same algorithm over here, and then I can compute the answer for this as the node. So let's call it 1, let's call it 2, let's call it 3, 4, and 5. So you'll say that, okay, I can get you the answer if 1 is the node, I can get you the answer if 2 is the node, I can get you the answer if 3 is the node, or 4 is the node, or 5 is the node. Now let's say whatever algorithm you develop to get the answer for a particular node as the root, right? When I say as a node, I meant actually as a root. So I can get you the answer if 1 is the root, if 2 is the root, if 3, if 4, if 5. Now let's say your algorithm, whatever you developed, took order of n time complexity to get you this answer. So you'll say, okay, cool, I did it for in order of n, I got it for the first node. In order of n, I got it for the second node, considering this as the node. On order of n, I got it for the third node, and so forth. So let's say there are n nodes and you are processing each of these nodes, right? So you are considering each of these nodes as the root vertices and then getting me the answer. So we'll say, okay, the total time complexity now becomes order of n square, right? But what if we want to reduce it? So let's say we want to make it order of n, or maybe order of n log n, something that is at least lesser than n square, right? So if we want to do that, then it's not a choice for us to traverse the entire tree considering each node differently, right? So I cannot say that, okay, whenever I consider a different route, I'll traverse the entire tree again. I can't do that. So for these kind of operations, we require a more smart approach that is actually called tree rerouting. So what it basically does is that it will say that, okay, you already have the result if this was your node, right? Now let's say instead of 1, okay, let me reroute it. It would get messy otherwise. So let's say this is the tree. Cool. Okay, so you'll say that, okay, I have the result if 1 is your root, right? Now I'll say that, okay, let's say that 1 is not my root, but 2 becomes the root now. So what would happen? As soon as you go from this node to this node, a few things are going to change. For example, now this is just an example, there could be a lot more things as well. So the things that are going to change is that these two nodes are going to become closer to you. So let me mark it with black or white. So this node and this node are going to become closer to you, but the node 3 is going to become more distant to you, right? So this is one of the changes that is going to happen. Now similarly, there are like depending on what you're trying to find, you can like define the changes. So this was one kind of change that happening over here. Now I will say that, is it possible for me that I already know that, okay, I'm going from 1 to 2, right? So is it possible for me to calculate the result for 2? Now result of 2 basically means whatever algorithm we were deploying to get me the result for whatever question was being asked, right? So you said that, okay, I already know the result of 1. Is it possible for me to calculate result of 2 in a time complexity less than order of n? Cool. Because if it was order of n, then you'll say that, okay, I could have actually traversed the entire tree again and I could have got you the answer. So what's even the use? So is it possible for you to get the result of 2 or the result considering 2 as the root node in order of 1 time complexity? So that is the final goal, and this is what tree rerouting basically means. Now let's try to understand the CSES problem, and then probably this concept would become much more clear. So till this point, this is the basic definition. Any doubts? Cool. If you have any doubts, then let me know. Yeah, cool. Okay, so let's discuss the problem. So the problem states that you are given a tree consisting of n nodes. Your task is to determine for each node the sum of the distances from the node to all the other nodes. Now this basically means, so I can rephrase this problem and say that your task is to determine this this distance to all the nodes considering the current node as the root node, right? So that would actually mean the same thing. So this becomes a standard or a very typical DP rerouting problem, or no, not DP rerouting, but tree rerouting problem, or root rerouting, whatever you want to call it. Okay. So the first input line contains an integer n, the number of nodes. The nodes are numbered from 1 to n, and then there are n minus 1 lines, so which would describe the edges. So there would be edge from 1 to 2, which definitely would not be directed since it's a tree. And each line contains 2 integers. Yeah. So that's what they're saying. Now over here, they have mentioned that n can go up to 2 into 10 to the power 5. Now, if you are having an algorithm that is order of n or order of n log n, that's fine enough. But if you try to compute the entire distance again and again for each node, considering that node as a root, then a time complexity becomes order of n square, which would give you a TLE over here. So you got the point, what we want to do, right? So the problem statement is clear, I hope. Okay. No, Abhi, there's a problem. Okay, there's no problem. Cool. Okay, let's start with understanding that how we can do it. So what I'm saying is that let's say this is the tree, not red, but maybe yellow. Cool. So this is the tree I'm having. Now I want to calculate what is the distance from all the nodes from this node. So let's say this is the node 1, this is 2, this is 3, this is 4, this is 5. Or let's just make the entire thing that they have actually made. So I think this is the tree they have given in the test cases. So yeah, one is one from 1 to 2, then 1 to 3, then 3 to 4, 3 to 5. Yeah, this is the tree they have actually made, right? So let's talk about this tree. Now what would be a result of 1? Okay, yeah. So your result of 1 would basically be the distance of all the nodes from this node. So 2 is at a distance 1, 3 is at a distance 1, 4 is also at a distance 4 is at a distance 2, and 5 is at a distance 2. It becomes 1 plus 1 plus 2 plus 2, right? Which actually gives you 6. So result of 1 is 6. What about result of 2? Result of 2 is 1 is at a distance 1, 3 is at a distance 2, 4 and 5 are at a distance 3 and 3 respectively, right? So this would become 6 and 3, 9. Result of 3 similarly becomes okay, so 1, 4 and 5 are at distance 1, so that is 3 basically, and then 2 is at a distance 2, so this becomes 5. Let's say I'm going from 1 to 2, right? Then what would happen is that if I'm going from 1 to 2, let me redraw it so that you're able to understand it. So let's say this is 1, this is 2, this was 3, this was 4, this was 5, right? Now I already have calculated result of 1, but right now I don't have result for any other node, right? So what would happen over here? As soon as I go to 2, then this entire, or 2 is not a good example because it doesn't have a subtree, so all the cases won't be covered. Let's say I go to 3. So what would happen as I go to 3? So this particular subtree, or the nodes which are in this particular subtree, actually become closer to me. Okay, a centroid was drawn. Okay, so yeah, these all nodes actually become closer to me, right? What about this node? The nodes that were not in this subtree actually went away from me, right? What can I observe from this? So I can say that whatever nodes are in my subtree, they are becoming closer to me, and the node which is not in my subtree, or all the nodes, so basically n minus number of nodes in my subtree. Cool. So n minus number of nodes in my subtree basically means all the nodes that are there in the tree but are not directly in my subtree, those become away from me. So the basic concept of calculating distance is that as soon as you have another node, so what do I mean by that? So by that I mean that, let's say this is the kind of a structure you are forming and you wanted to calculate the distance from this, right? Cool. So as soon as one more nodes get connected over here, the distance increases. Cool. What do we understand by that? By that I can say that as we move away from a node, its contribution to the entire distance increase, because as we move away, so that means we are adding one more edge, correct? So since we were over here, we are moving away from 2 and we are also moving away from 1. So when we are going from 1 to 3, we are technically moving away from 1 as well as from 2. So that would mean in the distance of 1, one edge is added, and also in the distance of 2, one edge is added, right? So what would be the addition in the distance? So addition in distance would be the one edge that would be contributed by 2, and one edge that is contributed by 1. Because in the actual distance, you will say that okay, now 3 to 1 is actually having a distance 1, and 3 to 2 is actually having a distance 2, right? Initially you were saying that 1 to 1 actually has a distance 0. That's obvious, right? Standing at 1 when I was calculating the distances. So I was saying 1 to 1 has a distance 0 and 1 to 2 has a distance 1. But now since we move to 3, so now one edge gets added extra, right? So now we say that I'm not going from 1 to 1, rather, okay, let's try to write that up. So yeah, you were initially saying that you are going from 1 to 1, so distance is 0. You're going to 1 to 2, so distance is 1. Then you were saying that you are going from 1 to 3, right? The distance is 1. Then you were saying you're going from 1 to 4, distance is 2, and 1 to 5, the distance is again 2. But as soon as now you say that okay, I'm gonna go from 1 to 2, 1 to 3. So now what happens is, let's replace 3 with 1. So over here 3 would come, right? So let's mark the nodes that are going away from you. So over here 2 nodes are going away from you. These 2 nodes, right? That is this particular node, that is node 1, and node 2 are gonna go away from you, right? And these 2 nodes are gonna come closer to you. Now, and also this node. So yeah, this is the root node itself. So this has the distance 0, but anyway, let's consider that. So as soon as these nodes go away from you, what happens is that you'll say, okay, so now 1 is no longer in the picture. So I have to go from 3 to 1. Because of that, 1 node extra gets added to my answer, right? So its distance become 1. Now I have to go from 3 to 1 to 2, right? Because firstly I'll be reaching out 1 and then I'll go to 2. So its distance also increases by 1. This becomes 2. But now I need not go from 3 to 1 and then to 3 again, right? So I'm directly at I'm at 3. I wanted to go at 3, so its distance is 0. When I want to go from 1 to 4, I need not go from 3 to 1 and then 1 to 4. I can directly go from 3 to 4. Its distance also decreases by 1. Similarly is the case with 5. Its distance also decreases by 1. Cool. Is this understandable? Any doubts so far? And yes, when we sir. Okay, cool. So when we sum this up, we get a distance of 5. Now would we so basically the understanding from this is what I said earlier, that you can calculate the number of nodes at each level. That is doable, right? In a recursion call, we can populate this vector at least. So considering that our tree is rooted at a certain root, any root that can be, for convenience we'll take root 1. So number of children in each subroot can be calculated, right? Subroot. That can be calculated for each of the nodes in a DFS call. That is easy. Then what I'll do is that if I'm coming from a parent P to a vertex U, then I'll say that the result of U would actually be whatever the result for P was, right? Plus you'll need to add the nodes that are not in your subtree. So that would be n minus number of nodes in your subtree. Minus 1 because your node also needs to be considered, because your node actually came closer to it. When I'm saying number of nodes in your subtree, if you're considering this, okay, so let's say this is the subtree, and over here if you consider 1 to be a part of the subtree and you're counting that, then you need not subtract 1. But if you're not doing that, then subtract 1. Now plus whatever nodes, okay, so you already added them, right? So no worries. Yeah, now you need to subtract some value. So what value would be you'll be subtracting? So you will be subtracting the number of nodes in your subtree, right? Because these are the nodes that are coming closer to you. These are the nodes that are going away. Let's code it up. Firstly, I'll write the algorithm where we are going to use. So I actually need a vector, that is the node count vector. This would tell me the nodes in each subtree. What do I mean by each subtree? Considering, okay, so let's say node count I would tell me nodes in the subtree of I. What do I mean by that? Let's look at that. So okay, if I go over here, then I was already a root I was having, right? I already selected 1 as the root. Then let's say in this particular subtree 3 is the root, right? And it has 3 nodes in total. This subtree has 3 nodes in total, and where 3 is the root. When we consider this entire tree, then we say that 1 is the subtree and the number of roots are 5. If we consider this subtree, then okay, 2 is the root and the number of nodes is 1. So that is what I mean by that. And the next thing we are going to need is the result vector, right? So this basically contains our answers. So we are storing it because at the end we need to print them sequentially. So we got to store it somewhere. So how would we populate the vector? So firstly, let's populate it. So let's call it DFS traversal, right? Or let's call this method populate. What it will have is a node, right? It will have the graph also, and then it will have the parent. So this is a similar DFS traversal. Let's look at the functionality later, but let's take the input first from the system. So this is the very standard code. Yeah. So I have the boilerplate input taking mechanism or input taking code in my snippets. So I'll be using that. So over here, edges is n-1. Then you take the input. Then you call this function populate with the node you want to set as root. So you can set any node for that matter. I'm setting 1 as the root over here. Then you pass the graph, and then you need not pass the parent because I'm taking a dummy parent over here for the first root or the first node, that is the root. Then I'll have to start the DFS traversal. But before starting, so can I do something with the node count? So I know that the current node is always a part of the root node, is always the part of the current subtree, right? So let's mark it as 1 because its size has to be 1. The current node is always a part of it. Let's mark it as 1. Also, let's just take the vectors. So I'll be having the vector node count. The other vector is res, and also give them sizes. So node count dot assign n+1, right? The default value is 0. Okay. And the same would be for res. Cool. So once I'm over here, then I'll say that I'll traverse for all its children. So all the children that are there in the graph of node or which are adjacent node, the only condition is that it shouldn't be the parent itself. Otherwise we'll fall into loop. If that's the case, continue. If that's not the case, then I need to check, right? So how do I check? I'll not check, but I need to proceed further. So I'll go to child node. I'll set the graph to graph, and the parent would now be the current node. Once I'm done with that, so I would have populated the values for my child node. Now I can say let's update the current node. Now how would we update the current node? Now the node count, node count for the current node would also contain the subtree of its children. So that would be you'll add that value. You'll say it should add the value of the node count of its child C or CH. Okay, so you'll say CH over here. That's fine. Then you'll say that the result of the current node should contain the result of the child node. Plus this is one level away from it. So all of its nodes are also one level away. So you'll have to add one for each of those nodes, right? So you'll say result of child plus node count. Okay, node count of CH. I hope this makes sense, right? After that, we'll return. Okay, we need not return from this. So yeah, after this is done, I would already be having values for the res and the node count. If you want to check it, you can print some values to verify the claim. So you can print the value for, okay, let's just check result count for all of them or node count for all of them. So yeah, let's just print node count. Okay, let's see this. Okay, it says that, okay, so it's starting from 0. That's not required. It's one base indexing we are using. So, okay, so the very first node has 5 children. The second node has 2 children. Then the third node has 3 children. The fourth node has 1. The fifth node has 1. Or not children, but the number of nodes in the subtree. So that's correct. Let's also, so by this time, you in this particular function, you already consider that 1 is your root node, right? So the result for 1 should already be correct. So we can try to print the result of 1 and check if the value is fine. Okay, result of 1, let's check that. Okay. So yeah, result of 1 is 6 and it was expected to be 6. So that's correct. We can move ahead now. Now what do I want to do? I want to populate for other elements as well. And I want to do it in order of n time complexity. In order of n time complexity, I want to populate the result for all of these children. So let's do a DFS traversal for that too. So let's say int node. Then I'm gonna have the graph and then the parent initially set to -1. Then I'll say that, okay, I've already calculated it for the root node, so I need not calculate it further. So if p is not equal to -1, that means I'm not currently at the root node. Then only I'll do some processing, or I'll try to get the data for the current node. So what will be the result for the current node? Basically, it would be the result of its parent. But now, when you're coming from a parent towards your current node, all the nodes that are in your current subtree are actually becoming closer to you, right? So you'll have to subtract that value. So you'll say whatever node count was, okay, child count, okay, node count, not child count, node count of u, that is node, plus. Now, when you did this, you actually became more distant towards all the nodes that were not in your current subtree. So in order to calculate them, let's have a look at the current. Okay, let's just have an idea about the number of nodes in the entire subtree. Since we were using a one-base indexing, so the number of nodes would be represented by the size of the graph -1, right? And then we can say n minus whatever your node count is, right? Node count for this current node is, or this current subtree is. So if you subtract that, then you'll get all the nodes that are not in the subtree. So these are the nodes you are going more distance from. These are the nodes you are getting more closer to. So this basically becomes result of node is equal to result of p minus node count of, okay, minus nodes you are coming closer to, also known as the nodes in your subtree, plus nodes you are, okay, moving away from. Cool. So yeah, this is a one-line computation that should work. Let's see. And then after that, you'll say I'll have to do this thing for all the children as well, or all the nodes. So I'll say I'll try for all the childrens that are in my graph. And I'll have to check if my child is actually equal to the parent. That means I'm getting stuck in a cycle. So if that's the case, continue. Else, you'll say that, okay, run the TFS traversal for this current child. Consider the graph given, and then the parent would be the current node. So you'll do this. Once you're out of this, you'll say, okay, I want to, okay, so DFS 1G. And then after that, you'll say I have to print the values from 1 to n. So int I equal to 1 to I is less than equal to n. Okay, sorry. I plus plus, we'll say res I, get the space. Once over here, then we'll just say /n. So this should be good. Let's test this. Okay, yeah, the code works. If you want, I can try submitting it. Let's try to submit this. Choose a file, and this is tree distances 2, I guess. So let's say tree distances 2. That's over here. Let's check that. So yeah, the code works, and the code was neat, I guess. That was not a big mess. We were just using a function to populate it, and then another function to calculate it for all the children. This is actually the heart of the algorithm, which is doing all the work, right? I hope everything was clear. If there's still any doubt, you can always let me know in the comment section below. Cool guys, thanks a lot for watching this video. Bye bye.